This is not an FFT, and whether you think you know what an FFT is or not, you'll know way more than almost every single professional audio engineer on the subject by the end of this relatively short video. Consider this a free mini course. So FFT stands for Fast Fourier Transform, and what is it? It's some math shit for nerds. But why do we care about this in audio? Well, if you've ever used FabFilter Pro Q, Room EQ Wizard, Melodyne, Soothe 2, Isotope RX, none of those plugins would exist without FFTs. So whether you want to see the frequencies of your audio on a spectrogram or perform some kind of spectral processing on your audio, you need to change your audio from looking like this from the time domain to looking like this in the frequency domain. And that's exactly what an FFT does. In fact, the ability to switch from the time domain into the frequency domain is a major advantage of modern digital signal processing, but it's not a one-way street. You can use the inverse Fourier transform to go back from the frequency domain into the time domain again in a round trip transparently. So this is pretty much modern magic, and that is the magic that enables plugins like Soothe 2, for example. The math which gives you the magical ability to switch domains, as already mentioned, is called a fast Fourier transform. But why is it fast? Is that a non-fast, a slow, regular Fourier transform? Well, yes, there is actually, and now I'm going to tell you how a discrete Fourier transform works, and I'm pretty confident that this is going to be the first time anyone has ever actually explained this in the history of YouTube in the audio niche, because there's plenty of videos which are super math heavy on the topic and they're focusing at pure math university students, but I'm going to explain this in a way that us audio people are actually going to be able to understand. So we have an input signal which is a sine wave of an unknown frequency which we'd quite like to find out the frequency of. How do we do that? Well, we can test the correlation with another sine wave which we know the frequency of because we produce it ourselves. So let's say we have another sine wave here, or we could do even lower frequency than that, or we can go even low. What's the lowest frequency that we can go before going negative? That's right, 0. And that's DC. So let's put sample points on here. So let's just put 4 sample points on here, and we'll put the same sample points on here. Now, the way that we test a correlation is by multiplying the two signals together and then adding up the resulting samples. So I'll just tell you the values here. 1, 1, 1, 1, because it's DC, it's all the same, it's all just 1. And this is 1 minus 1, 1 minus 1. Now, what happens if I multiply these signals together? Well, as anyone should know, if you multiply a number by 1, you just get the same number, nothing changes. If you multiply a million by 1, it's still a million. So in this case, nothing changes. And if we then add up the sample points, what is 1 plus minus 1? 0. So if we add these up, we get a 0. The output is 0. And that's good because it means there's no correlation between these two waves. And you might think, okay, but how does that work? Well, we'll see when we start increasing the frequency of this. So we start low and then we start increasing the frequency of our test signal from DC to something still quite low. Now, the signal that we are using as the test signal is going to be always remaining positive, like it's got a DC offset. So it goes from 0 to 1. So right here, it's 1. So it's just the same as when it was the DC in the previous example. But then it starts going down to 0. How is that going to look? Well, at 1, it's just going to be the same wave as above. But then it's going to get quieter and then go like this and then fizzle out and be silent here. So let's say our sample points now are like 1, and this one's going to be like minus 0.8 or something, and this one is going to be like 0.6 or something, and then this one is going to be like minus 0.2 or something like that. And let's add all of these up. We might get something like 0.6 or something. So it's not 0. We've kind of made the number slightly higher, but it's still quite low. So we keep on increasing the frequency of our test signal and getting higher and higher and testing the correlation until eventually we stumble upon the same frequency as the input signal. What happens now when we multiply this out? Remember, this is from 0 to 1. So on our first sample, we're going to get 1 times 1 equals 1. On our second sample, we're going to get 0 times minus 1 is 0. Our next sample is going to be 1 times 1 is 1. Our next one, it's going to be minus 1 times 0, which is 0. So now we can add that up. Our result is 2. So what happens is, the closer the frequency is, the higher the number which is output. So we can visualize this a bit better now. So in the time domain, we have our input signal, which is a sine wave of an unknown frequency. But in the frequency domain, we have here 0 hertz, which is DC. And let's just say this is 10K or something, which is a higher frequency. And this input unknown sine wave falls somewhere in a frequency spectrum here. And let's say that we test all of the correlations, and at DC it's 0, and at 10K it's very close to 0 as well. And here it's a bit more, but it's basically 0, and it's a bit more here, but it's basically 0. And then you keep testing it, and then all of a sudden it peaks up here, and then it falls back down there, and it falls back down here, and it goes like this. Well, we can see that this is what an FFT normally looks like, something like this. If you've got a sine wave, we can spot that that sine wave is at this frequency here. And that's exactly what an FFT looks like. So we test all of these frequencies with a known sine wave. We're testing the unknown frequency. And then when we find a correlation, boom, we can spot it on the FFT. And that's how it works. It's really quite simple, but quite clever.
So that's pretty cool, right? The underlying math has got a lot to do with pi and circles and sine waves and stuff like that. And I simplified that explanation a bit because you don't only just have a sine wave, you also have a cosine, and that's just a slightly delayed sine wave, because otherwise it depends on luck whether the input signal is going to line up with your test signal. And if you use two sine waves, like a cosine and a sine, they have different phase rotations. So you can catch stuff that would otherwise be like hidden from the test tone. Like imagine one of those wind chickens that spin around based on the direction of the wind. If the wind is blowing straight on in the direction that you're looking, then the chicken basically disappears because you can't see it, because it's right on that axis. But if you look from the side, then you see the chicken again. And that's what the cosine gets to do. It kind of looks from different angles so you don't miss anything. But the problem with the approach that I just told you, testing the input signal with 1024 different sine waves and then a further 1024 phase rotated sine waves, and then adding all of those numbers up, this is obviously a lot of computational work for the computer to do. So that's not so suitable for real-time audio, and maybe modern computers can now do it, but back in the 90s or whatever, no chance, and you don't want to waste more CPU than you need to. And the second you start ramping up the sample rate and you've got a few FFTs on the go, it might be like billions of calculations per second for your computer, which is obviously dumb, and it's going to melt your CPU. So that's where the fast Fourier transform comes in. And it's not just some kind of estimation which cuts corners, it's the exact same result. But instead of going through and doing it step by step like I just described, you use some math magic to speed things up. And if you just so happen to want more insight on what that math magic is, you're in luck, because I'm now about to explain how the core logic of an FFT works. I'm actually not going to do that because I watched it back and it was so geeky that it would just bore the socks off of almost everyone watching this video. Phase correction, twiddle factors, pre-calculated butterflies, and twiddles. But as I've now interrupted the video anyway, I thought I'd make a quick announcement. And as most people know, I've got a whole bunch of courses on my website and plugins, but one of the plugins which I would recommend grabbing if you haven't done so already is Class A, because I'm going to release version 3 quite soon. It's currently on version 2. I already put the price up, and I said buy it before I put the price up, and then a few people were like, oh, I don't know, I'll buy it later. Then I put the price up and released version 2, and everyone was like mad because I put the price up. Well, I'm going to put the price up again because I'm releasing version 3. So if you haven't already got version 2, buy it now before the price goes up. And the same thing with curvature. A bit more time before I release the next version of curvature, but there is a new version of curvature coming too. And if you don't know what curvature is, it's the best compressor plugin in the world, and version 3 is coming at some point, and it's going to be even better, never seen before features, and the price is also going to go up, so buy it whilst you still can at this price. I just described the Cooley-Tukey approach, and there's other approaches, but that's the most classic one that is often used. But if that seemed a bit too complicated, don't worry, it is complicated, and it's more information than most DSP devs actually understand, because almost nobody writes their own core FFT logic. Almost everyone just uses existing implementations. But now let's get back to something a bit more intuitive. So what I've been describing up until this point is using a rectangular window and then doing an FFT on the rectangular window. But the thing is, rectangular windows suck. The reason is because the waveform gets chopped off at the boundaries. And when you just hard cut audio, then you get distortion, right? Anyone knows that when you edit audio and you just like cut it without a crossfade, it pops or it makes some kind of glitch, right? So the result of doing an FFT with a rectangular window is crazy distortion, and you get what is called spectral leakage, and it looks and sounds shit. So what we need to do is crossfade it to get it smoother, and to do that we use what is called a window function. And if you head to Wikipedia, I don't normally like Wikipedia, but in this case there's some really nice images of the differences between the different windows, and we can have a look at those now. So as you can see, if you use a medieval rectangular window, just hard chopping off the audio at the sides, it does work. You can see the frequency on the chart, but you've got crazy spectral leakage here. All of this here is just noise and distortion, and we don't want to see that. Ideally, we just want to see a really clean, pinpointed frequency. If you just do a linear caveman crossfade here, just standard, bog standard caveman linear crossfade, and make a triangle window, it's way better. It's a massive improvement. You see all of this noise and distortion here, massively improved here, just with the triangle. But it gets way better when you start doing a bit more kind of smooth, nice shapes, like minus 120 dB suppression at the extremes there. And you can go all the way through and look at all of these windows. Hand windows, quite a popular window. And then Blackman Harris is pretty much probably the most popular that is actually used, and you see that minus 120 dB rejection at the extremes here, so it's really used a lot. And you've got all of these different types of windows with all their different trade-offs, and then you can see the shapes here and the kind of the accuracy that produces over on the right hand side. And it's quite interesting that just modifying the shape just slightly can really influence the result. But the Blackman Harris window is one of the most popular ones. But again, as everyone knows who has done any audio editing on their computer, if you just split an audio file and then crossfade it there and crossfade it there, well, you're going to have silence in the middle. It's going to fade out and fade back in, and you're not going to have anything in the middle. It's going to be kind of like a null point in the middle. So you not only have to crossfade it, you also need to overlap it, because if you don't overlap it, you're going to be empty in the middle. You need to fill that in by overlapping it. And you do that when you're editing vocals. Everyone knows who's done any audio editing that you need to overlap, right? And the same thing is with the FFT. And so not only do we need to calculate the window, we need to calculate an overlapping window and another overlapping window, and going along like that. It's called a sliding window, that we have to recalculate the same kind of FFT, but just shifted a bit more and overlapping. And that's how we can crossfade it and get a high resolution FFT. And if you do all of that right, now you've got a basic FFT-based spectrum analyzer, and many plugins use this kind of approach. But you may notice that if you look at one of these kinds of plugins, in the bass frequencies, the resolution is shit. And don't be fooled by the fact that there's lines joining the data points together. There's only just a few data points in the low frequencies. And any audio plugin which has poor low frequency resolution on the spectrum analyzer is a badly coded plugin. It's a demonstration that the plugin developer who designed it doesn't know what they're doing. The reason for this is that frequency bins are spread out in a linear way with an FFT. So if you have a window length of 1024 samples, which is pretty normal, the bins are going to be spaced around 43 hertz apart. So you have the first one will be 0, meaning DC, the next one will be 43 hertz, and then 86 hertz, and then 129 hertz, and then 172 hertz. And you can see that in the base frequencies, your sub resolution is basically 2 data points, which is obviously shit. So whereas in the higher frequencies, you're going to have something like 21,880, 21,923, 21,966, 22,009, 22,050. Like, no human being could possibly want that much detail in the high end on a spectrum analyzer, because if your plugin is 800 pixels wide and the chart is displayed in log format, the data points will be a fraction of a pixel wide on the top end, and it'll be something like 100 pixels between each bin, between 0 and 43 on the low end, which is obviously dumb. So the way that you get around that is by having a bigger window, and then you can squeeze more bins in. You get more data points on your chart. Let's say you have something like 16,384 sample points in your window, or that will force more resolution into the base frequencies. But the problem with this is that at a 44.1 sample rate, 16,384 samples takes around a third of a second. And that's really slow if you actually want to see responsiveness in your higher frequencies. This is going to move too slowly. So there's a physical trade-off. Either you can have fast, responsive, snappy higher frequencies, or you can have good resolution bass, but you can't have both at the same time. You can't have your cake and eat. So this is maybe later year undergraduate tipping into postgraduate kind of level. It's not the most difficult thing in the world, but most people in the audio industry at least don't really have a clue about any of this stuff. So if you made it this far into the video, well done. You know more than most people know on this subject.